Hi, and welcome to this webinar. Today we will discuss the basics and key aspects of modal analysis, one of the key solutions in vibration engineering. We'll start with some examples of the effect of vibrations and how they manifest. We will look at how modal analysis is used in practice to design better products. We will then discuss the basics of modal analysis and the practical meaning of the fundamental elements, the modal parameters, and link them to the behavior of our structure. Finally, we will present experimental modal analysis and how the same method can be utilized to analyze the dynamic behavior of structures in operating conditions. Let's start now with some examples. In this first example, we will look at vibrations generated on a glass by some noise. If we play a tone, which is a noise at a specific frequency, it will cause the glass to vibrate. At some particular frequencies, the vibrations will be magnified significantly compared to others, and the glass will start deforming with a specific pattern. If we now increase the volume of the tone and excite the glass with higher power, the deformation of the glass will keep on increasing until it will eventually break. Now let's move to a second example and head to London at the time the Millennium Bridge was opened. As soon as people started walking on the bridge, it began to oscillate heavily. As people felt the oscillations and started to act against them, the motion actually kept increasing. Luckily, the bridge didn't collapse and no one got hurt during this incident. A typical example we all experience every day are vibrations of rear-view mirrors, either on motorbikes or cars. It's a very annoying effect, and it is caused by the transfer of vibrations generated by the engine or the road. This effect will change depending on the speed of the vehicle, on the engine regime, on the gears. It's extremely important for vibration engineers to minimize visual blurriness in as many situations as possible. And finally, let's take a look at this aircraft. It's clear that in this specific operating condition, the aircraft is twisting around its main axis. Both wings and horizontal tail planes oscillate rather violently. What's happening to the glass, the bridge, the rear-view mirror and the aircraft is that the external loads are exciting a specific mode of the structure, making the response way higher than it should normally be. Modal analysis is a key tool to help understand and controlling this phenomena. In the rest of this session, we will try to clarify how it is possible to analyze and control these phenomena. But let's first take a look at the general reasons why modal analysis is important and what benefit it brings to the industry. Modal analysis is well accepted and widely used in industry. It represents a center pillar in product development. The approach is used throughout the development cycle during design, production, validation and troubleshooting phases. During the design phase, it helps defining clear targets and allowable performance boundaries. For example, a specific mode should have a frequency in a very narrow band to maximize comfort. Alternatively, it can be used for benchmarking and thus gaining deep insight into competitive products and provide an answer to the question, why do they perform better? Secondly, modal analysis gives you a set of objective and invariant quantities, which can be used to validate and improve numerical models, more particularly finite element models, but also to verify some design assumptions. Thirdly, once a prototype has been built, dynamic analysis can be used internally to the company to verify that the targets defined during the design are actually realized. Moreover, as is the case for aircraft, a modal survey test needs to be performed for certification purposes. Finally, if excessive noise or vibration levels are experienced once the product is in operation, very simple and quick tools are available to detect and characterize the source of the problem. The user can then propose local modifications by, for instance, adding some stiffness or damping on specific panels. And we can quickly estimate what the effect of these modifications will be on the global response. As mentioned before, we will start by explaining the practicalities of modal analysis. What is modal analysis all about? We will introduce the most important elements, the modal parameters. We will also explain the principle of experimental modal analysis, and after that we'll explain how they can be extended to the analysis of structures in operating conditions. Let's start with a fairly simple definition. We can define modal analysis as a process of characterizing the dynamic behavior of a structure to explain its vibratory response. But what does this practically mean, and how is it useful for improving my design? Using modal analysis, we can represent each and every engineering structure, from buildings to satellites, from ships to cars, as a set of constitutive and simple elements. All of these elements represent a particular structural property and are fully described by three parameters, the modal parameters: the natural frequency, the modal damping, and the mode shape. Real structures have an infinite number of modal parameters, but in practice we can consider a finite subset, which will depend on the frequency range we are interested in. The modal parameters, which can be looked at as independent elements, can then be combined together into a modal model, which represents an equivalent and practical description of the complete structure. They have the very important property of being independent of the applied load. They're simply a description of the structure. To explain the meaning of the different modal parameters, let's consider the simplest possible dynamic system: a rigid mass connected to the ground by an ideal spring of stiffness K. If we apply an impulse force to the system and we measure the response, we will observe that this system oscillates at a very specific frequency. This frequency is a property of the system, and in this simple case it can be computed analytically by simply taking the square root of the ratio between the spring stiffness K and the mass m. Instead of looking at the time data, we can convert all of this to the frequency domain by taking the fast Fourier transform. We can now see that the impulse input results in a flat spectrum, and all frequency lines are equally excited. If we look at the response, we see a very sharp peak. What this tells us is that if we apply a broadband excitation to the system, the response is dominated by one specific frequency, which is of course the natural frequency. By taking the ratio between the output and input in the frequency domain, we obtain what is generally known as a frequency response function, which is a description of how the system would respond to an input. The frequency response function, or in short FRF, shows what the amplitude and phase would be of a response given a certain input force at a given frequency. We can immediately see what happens at resonance. Even though we keep the excitation level constant, if we excite our system at a particular frequency, we got significant amplification of the response. This is one of the reasons why we perform modal analysis. We want to understand where the resonance frequencies are to make sure that we avoid excitation at those frequencies during operation. In the system we analyzed, an impulsive excitation would cause the system to continue to vibrate for an infinite amount of time. Also, the amplification factor at resonance would go to infinity. In real systems, obviously, there are forms of dissipation of energy, and this will change the frequency response characteristic of our system. Now let's take the same system as before and let's add a connection with a dissipative element, which we indicate as C. If we apply again the same excitation as before, the system will still respond at the same frequency as before, but what changes is that the amplitude now progressively decreases until the system goes back to equilibrium. The effect of damping is even more clearly visible if we convert again from time domain to frequency domain, calculating the frequency response function. In this example, we have progressively increased damping. It's immediately clear that by adding damping, the amplitude at resonance of the vibrations will decrease. The phase shift at resonance will also become more and more smooth. Because of damping, the actual damped natural frequency will slightly decrease with increasing damping. However, the undamped natural frequency will remain constant. Damping can thus be seen as a safety factor for vibrations, since it reduces the amplitudes, makes the system response smoother. However, while modal damping is defined as a percentage, and it's quite easy to understand it, mastering the physical mechanisms behind damping is generally quite complex, as it involves often nonlinear phenomena. The last modal parameter we need to discuss is the mode shape. To properly discuss this one, we need to add an extra degree of freedom to our system. We have now two masses connected by a spring. The system has now 2 degrees of freedom, which are responses of the two masses. If we now calculate the frequency response function, we can immediately identify 2 resonances at different frequencies. At this point, the definition of mode shape is extremely simple. Each mode shape describes how all degrees of freedom of a system move at resonance. In this case, the shape for the first mode will be the 2 degrees of freedom moving in the same direction, called in phase. At the second resonance, the 2 masses will move in opposite direction. This is out of phase. Mode shapes have 2 very important properties. First, if we assume the mode shape can be described by real coefficients, at resonance, each point will move in phase or out of phase. Secondly, mode shapes are always linearly independent. This means that even with a system with 1,000,000 degrees of freedom and thus 1,000,000 mode shapes, the correlation between any pair of different mode shapes will always be 0. Up to now, we've been looking at simple systems with a few degrees of freedom only and with lumped properties. However, real structures are continuous, which means that they have an infinite number of degrees of freedom. Considering continuous systems is not feasible, but we can still apply modal analysis either numerically or experimentally by deriving a discrete model of our continuous structure. Such discrete approximation will describe the system response correctly up to a certain maximum frequency of interest. We can perform numerical modal analysis by creating a model of our component or system, discretizing it into a finite number of degrees of freedom, a process called meshing. Those finite degrees of freedom, those elements, are characterized by material and element properties. We can define a mass and stiffness matrix, and from all of this we can derive natural frequencies, mode shapes, and frequency response functions. Damping is only seldom included in such calculations because it's very complex to model. Experimentally, the only thing we can do is measure. By measuring the motion or deformation at a discrete number of locations due to a known force, we can estimate the frequency response functions between those points. From those frequency response functions, it's then possible to identify natural frequencies, mode shapes, and in this case also modal damping. Experimental modal analysis will be further discussed later, but now it's important to stress a key characteristic of this modal analysis. End result of both numerical and experimental modal analysis are identical: natural frequencies and mode shapes. These properties are commonly used to verify that numerical models are representative of the dynamic behavior of the real structure, and update the properties if this would not be the case. Also, the experimental modal damping can be applied to the numerical models to improve predictions, avoiding the need to build very complex damping models. At this point, we need to introduce the formula which will close the loop between all basic concepts we've introduced this far. Each piece of the puzzle contains a natural frequency, modal damping, and mode shape. For a specific mode, the modal parameters can be used to calculate a corresponding frequency response function, as we show in the formula. The numerator is directly linked to the mode shape and the denominator to a system pole. This pole can be calculated directly from the natural frequency and the modal damping. As modal parameters are generally complex quantities, both complex conjugate terms need to be included. Q in the formula is a simple scale factor. A similar equation can be written for all identified modes. Because of the superposition principle, the overall dynamic response of the structure can be represented by a linear combination of the responses due to each mode. This apparently very simple formula is the basis of modal analysis. Also, it creates a link between the modal model, the FRF matrix, and the dynamic response of the system to an excitation. Let's now go a bit more into the details of experimental modal analysis. As we have already mentioned, experimental modal analysis consists of two processes. First, we will use experimental techniques to collect data on a structure. Secondly, we will use modal parameter estimation techniques to derive a modal model from the measured data. The whole experimental modal analysis process can be summarized in 5 steps. First, we will prepare the test setup, including instrumentation, and will define the test properties. Second step is to execute the test, collecting the data we need. Next comes the system identification, a step in which we will derive modal parameters from the measured frequency response functions. Next, we will assess the quality of the identified modal model. As a last step, we will use those results to validate numerical models, calculate force response, calculate coupled response, and so on and so forth. To perform experimental modal analysis, we need to record the responses at several points of a structure due to a known applied excitation at one or more locations. From this measurement, we can then identify the system frequency response functions. The first step is to prepare the instrumentation and the structure for the modal test. As this is an introductory webinar, we will only deal with the most common scenarios. There are several options the user can choose, and the choice between the one solution or the other depends on the test requirements, the complexity and the size of the test object, the weight, and also the budget available. To apply and measure the excitation, we can use impact hammers or electrodynamic shakers. In both cases, we will use a load cell to record the actual force. To record the response, the two most common sensors are accelerometers or laser Doppler vibrometers. Those sensors record the velocity. Accelerometers are most often preferred because of their flexibility. Laser vibrometers are used on lightweight structures or when a very high spatial resolution is required. The signal management, analog to digital conversion, digital signal processing, and synchronization are usually managed by a data acquisition system. Finally, an important choice for the test are the boundary conditions. Free boundary conditions are generally easier to realize, and they simplify the validation of a finite element model. Alternatively, fixed free boundary conditions are also widely used. However, ensuring that the clamping is rigid enough is not always easy. Sometimes the actual boundary conditions of the structure in use are the only possible solution, for example, when doing operational troubleshooting, or when doing a measurement campaign on a very large structure, such as a bridge. Once the setup has been prepared, data can be acquired. Depending on the type of test and the exciter used, different solutions are available, but in the end, they all apply the same process. From the time history of the inputs and the outputs, blocks are extracted, converted to the frequency domain, and then frequency response functions are estimated. To reduce the effect of noise and nonlinearities, which are always present in real structures, averaging is applied. The quality and repeatability of the averaged frequency response functions is quantified in the coherence function, which is regularly used as a validation tool to assess the measurement results. Once we measured all FRFs, the next step is to perform the modal parameter estimation, extracting modal parameters from the selected set. First step is to define the frequency range in which we want the modal parameters to be identified. We will not go into the details of the modal parameter identification algorithm itself, but the general principle is very simple. Find the combination of modal parameters which maximize the fit between the measured FRFs and the ones calculated from the identified modal model. It should be clear now why the fundamental equation was introduced at the end of the introductory part. In our example, we see in the selected frequency range 3 peaks, so we expect to identify 3 modes, 1 mode for each peak. For each mode, the frequency, damping and mode shape, together with the scaling factor, need to be identified. The green curve is the frequency response function recalculated using these modal parameters for this particular mode. It also shows the contribution of that same mode in the frequency range of interest. For example, it might be interesting to understand the contribution of the different modes in the response at a specific frequency that does not coincide with the resonant frequency. If the modes are well separated in frequency, at resonance, the response is normally dominated by the mode shape of that particular mode. Once we have the mode shape, it is very useful to animate this shape. If a geometry is available, we can have a very clear visualization of the deformation of our component at that specific frequency. We now repeat the same analysis for the second mode. And finally, for the third mode. Once we identified all the modes, we can combine them together and obtain an overall frequency response function over the frequency range we're interested in. At this point, an obvious approach is to make sure that the modal model we estimated is representative of the real structure and we didn't miss any modes. We will typically validate the identified modal model by synthesizing the resulting frequency response function and overlay that synthesized function with the measured one. From that overlay, we can calculate errors and correlation coefficients. This gives an immediate feedback on the quality of the model. If some modes are not included, this will be immediately clear and the user can go back to the identification phase, adding the modes to the model. In many modal analysis solutions, several validation tools are available. For example, how complex a mode is, or how sensitive a mode is to mass variation. This last parameter can be used to understand if the selected mode is a physical one, or rather just a numerical artifact with no physical meaning, merely there to reduce the error. Once we have identified and validated the modal model, the actual modal analysis itself can be considered as concluded. But what can we do with such a modal model? First, we can calculate what the effect is of variations of mass, stiffness and damping on the modal parameters that we've calculated. The sensitivities are approximative estimates, but they can be very useful in determining the most effective location for a specific type of structural change. Also, it provides very first estimates of the amount of modifications that are needed to achieve a certain change in structural behavior. Sensitivity analysis information is normally also used in modal validation and updating, but also to understand how and where modifications can be applied to a component if the response doesn't meet the targets. The next step is normally to apply local modifications and compare the modified system dynamic behavior with the original one. One can, for example, design a vibration absorber for a specific mode. Given, for example, the target frequency of the mode and then the mass to be applied, and it's possible to calculate the required stiffness and damping. Another very common application, in particular for very light structures, is to verify the influence of the sensor mass on the modal parameters. Probably the most common use of experimental modal model is to validate and verify numerical models. As we have already seen, modal analysis creates a direct and simple link between test and simulation. Matching the modal parameters is a clear objective to assess the correlation between the physical and numerical results. By taking advantage of sensitivity analysis and optimization algorithms, it's possible to update physical parameters to improve the model based on the experimental data. in the majority of the cases, the errors between the natural frequencies and correlation between mode shapes are used, and the results are summarized as seen here in these two diagrams. It is also possible to combine two modal models and predict the response of the coupled structure. This can be useful when we need to understand the influence of different variants of the same component on the behavior of the full system, without having to assemble and physically test it. This can be performed with either numerical and/or experimental models. The framework to combine component models to predict the coupled dynamic response is commonly known as dynamic substructuring. Within this framework, combining numerical and experimental components into an assembly for further calculations is generally known as hybrid modeling. A further step is then to run test-based simulations in which we can apply several load cases and predict the response of the assembly. As we have seen, standard experimental modal analysis identifies a modal model from measured frequency response functions. As we saw, the calculation of the frequency response functions requires that all forces applied to the system are measured. However, this might not always be possible. This is, for example, the case for the structures shown in this picture. It is extremely challenging to find a shaker that is powerful enough to apply sufficient force to this bridge or to the wind turbines at the right. Similarly, how to derive a modal model for an aircraft in flight. Being able to identify a modal model on those types of structures in operating conditions would, on the other hand, be extremely useful, in particular to have an estimate of their actual damping values, and consequently improve the accuracy of, for example, fatigue life calculations or flight stability calculations. To cover those cases, operational modal analysis was introduced in the 90s. This allowed identifying modal models from structures being in operation, relying solely on response measurements. It is applicable in those scenarios where the forces acting on the system have a random profile, meaning their frequency response is flat. In those cases, similar modal parameter identification algorithms exist. If the excitation profile doesn't comply with the requirements, the estimated modal model will be less reliable. An extension to operational modal analysis is order-based modal analysis. The method was specifically developed to identify a modal model for rotating machines in operation. Here, the assumption is that the dominant excitation is generated by a rotating component. By measuring the rotational speed of the machine during a run-up or coast down, orders can be extracted and standard modal analysis algorithms can be applied. Also in this case, the advantage of this method is that it provides an operational modal model of a structure, and it allows identifying the actual operational damping values, which would be very difficult to impossible to estimate reliably in non-operating conditions. In this seminar, we've explained the fundamental concept behind modal analysis. We have seen some practical examples and how modal analysis is used throughout the industrial product development process. After introducing the concept of natural frequencies, modal damping, mode shapes, frequency response functions, and how those are heavily interconnected, we discussed the main steps in experimental modal testing and analysis, from instrumentation to validation of the modal model. Finally, we got a quick glimpse at the methods available to identify a modal model in operating conditions, where the forces acting on the structure cannot be measured and thus frequency response functions cannot be obtained. I hope this web seminar was interesting for you. I'd like to conclude by thanking you for taking the time to follow along.